Good morning, everyone. What we're going to do today is return to libc technique for bypassing data execution prevention, DEP, or NX. So what we're going to do, I have a simple C program here, and it's just, we're using stir copy, which is vulnerable to, it doesn't do bounds checking, so it's vulnerable to overflowing a buffer. We have our buffer set up here at 256 bytes, and this is just a little main and a vulnerable function for us to play with. So first things first, let me get to my working files here. And I already have DEP compiled, but I'll do it again for you guys. So we're going to use GCC if no stack protector. This turns off the stack cookies, and we'll get into bypassing stack cookies and that later as well. Usually we put exec stack in, which would turn DEP or NX off. We're going to leave that out for this one. We will do no pi, and we will then take dep.c, and I'm going to output it to DEP as an executable, and that's what we will haul apart. And everything compiled well, there's no bad messages there. So what we will do now, we will, I have a draw IO that goes along with this program as well. So this way, when I'm teaching larger classes, no one's going to mess up the inputs, which actually slows the class down and causes a lot of trouble. So first things first, we're going to open up PETA extension. I like using PETA for this one because we can grab the gadgets directly from inside PETA. So let's do check sec. And this will show what protections are being used on the binary. And as you can see, NX is enabled, okay? So ASLR is off right now, NX is enabled. So we're going to bypass DEP. So let's disassemble the main function here. And as you can see, luckily we have a thing called a vulnerable function here, and it's labeled as such. So as reverse engineers, that's lovely. Next, we're going to get to the stir copy. So here's the stir copy that copies our input into the buffer right here. And this is what is vulnerable to the buffer overflow. We can also see things like gets and scanf and such, but we will get into that at another time. So I'm going to set a breakpoint right at the call for stir copy. And then I'm going to run the program with an input of 20 A's. So we just had to use a little Python here to run it. Python 3 is a pain in the fucking ass for doing this. So having it written out like this is a lot easier for students to follow. So as you can see, so if we just come and have a look for 80 words in hex from the stack pointer, the ESP, we can see our full stack right here. So let's have a look at where the base pointer is. So the base pointer is at EF98. So EF9, so 0, 1, 2, 3, 4, 5, 6, 7, 8. So here's our base pointer. This right here, if we just do XWX, examine the words in hex of this right here, as you can see, that's our main function. This would be argument 1, this would be argument 2. So what we have to do, we have to fill this buffer right here up with A's, right up to our base pointer, which is right here. Now to bypass DEP, what we're going to have to do, we're going to have to overwrite the return address with system. So when the program does crash and goes back to the libc library, it'll invoke system. We have an exit function for it here, and then argument on argument 2, we're going to place the bin sh. So the system's going to pop bin sh, which will pop a shell on the system. So this is the return to libc method of doing this. Okay, so if we just hit next instruction, and let's have a look at this again, and you can see our 41s, which is our A's, have been placed here on the buffer. And we're quite a ways off from right here overwriting this here. Now we could fuzz it like we did in the last one, but what we're going to do is just we're going to continue on, and then we're just going to place a larger buffer in. Let's come along here and let's run it again with a larger buffer. Our breakpoint's still set here, so we can do, let's have a look at the buffer again, and as you can see, there's nothing in there. We hit next instruction. Let's have a look at our buffer again, and as you can see, we're quite filled up. So instead of fuzzing it, I knew 280 would definitely overflow it, but we've overflowed it. So here is the base pointer we need. So this is correct right here. So we need to take 4, 8, 12 away from 280. So that'll bring us down to 268. So let's continue on here. Okay, so let's put in another buffer here of 268 A's and just hit next instruction. Let's have a look at our stack again. And as you can see, all those beautiful A's have filled up everything, including the EBP right here, our return address right here. Now this is where we're going to put system. This is where we're going to put exit on argument 1, and on argument 2 in our buffer, we're going to put bin sh. Okay, so we have that figured out. So now what I'll do is we'll take our input, and as you can see, I have B's, C's, and D's. So the B's are a placemat for, or skeleton for our system, C's, the exit function, and D's for our bin sh. So that all lines up good. I'm just going to continue on our program here. And SIGSEV, of course, we've overwritten the EBP, so it's given us a segmentation fault. So now we'll run this again, and of course we hit our first breakpoint. Let's have a look at our stack again before everything gets put in. And as you can see, there's nothing. Let's hit next instruction and hit our stack again. So all our A's are aligned right up to EBP. EBP is covered. Return address, where system will be going, is covered in 42s, which is our B's. Our C's is on argument 1, and our D's, which will be bin sh, is on argument 2. So everything is lined up copacetically. There's no problems there. So what we'll do now, we'll open up a notepad and just put this down here. Now, there are various ways to finding gadgets and such. This is a nice simple way using PETA. We can just print system, and here's our system address from the libc library. So this is return the libc method. Next, we're going to, for our second, we're going to need the exit function. So let's have a look here, and here's our exit function, and we'll place that on the stack. And then we need to find bin sh. Now, whatever you do, do not forget this first slash, because bin sh is different than slash bin sh, and it won't work. So here we go. So now we have our bin sh. Lovely. So now we have that placeholder. So what we're going to do is we need to make this into a binary file. So we just take our input we just had, and as you can see here, let me just hit enter here just for the sake of making it easier to see. As you can see, we put this in backwards. You can see 2039 DD B7, little Indian format, right? Let me write bin sh here for clarity. And then we look at our exit function, 60 goes in here, 2D, so they're broken into groups of 2 and read backwards. Okay, so you can use the struct library for this as well, but I have it in this simple binary. And then bin sh AA cf and f3 and b7 right here. And then we're going to send that into a file called payload.bin. So what I'll do, copy, and we will exit out of our PETA. I'm going to place this, and then I'm going to hit that. Exit. Hold on one sec. I have something wrong there. I forgot the first part. Here we go. Let me just grab all this. Just give me a new open tab. Here we go. So let's try this again. So now I'm going to just port this into a file called payload.bin, and we're going to use this to do our exploit. With Python 2, I just used to be able to put this in a print statement and put it in, but there's been so many changes to Python 2 to 3 that I've had to go about things a bit differently. Let me also post this back in here. Sorry, guys. Copy and paste. Okay. So next, what we're going to do, we're going to run the GDB with this as an argument. So what we will do is come here. Now the name of the file is DEP, and actually I'm going to take the second from you guys to change this here as well. Okay, so here we go. So now this is going to run our file with this as the payload outside here. So we're right back to the beginning. We're going to disassemble the main again. And let's disassemble vulnerable function. And let's put a breakpoint. Copy breakpoint at our stir copy. And then we hit run. And you can see our input is all gone in. So now I'm going to do X. Give me 80 words from the ESP. And I can see nothing's put in there yet. Let's hit next instruction and have a look again. As you can see, all our 41s are filled down. Our return address is overwritten with B7DD3920, which is our system function. If we come here to our argument 1, it's overwritten with the exit function B7DC2D60, perfect. And our last input, B7F3FAA. We are golden. So if we continue on here, as you can see, detaching from fork after child process, who am I? Wordly ls-l, we have shell. So that is how you bypass data execution prevention, the old school return to libc method. There are different ways of doing this now, especially with more sophisticated binaries and such, but this is a good starting place for everyone to learn. So I hope you enjoyed that. That's bypassing DEP, and I shall get back to you guys really soon on bypassing DEP and ASLR at the same time. Okay, look for that video in the next couple days. Bye.